All right, let's get started. I don't really have much in the way of major announcements, but what I will say is this. You have homework 3, which is due on Monday, but let's talk about that. So Monday, we are going to have exam review, and then what do we have on Wednesday? We have an exam, okay? So I'll say a couple things about that. The one thing is this, so there's a good chance I will try and end concrete design a little early that day to give you all a little more time. But that means you gotta be here. Who, other than concrete design, who has class right before this? How many? Like, I need to see your hands high up in the air. Okay. All right, so a few of you. So what I can try and do, I don't know about you all, but how would you like it if I started the exam at 10:50? Could you do that? Okay. We can start, how about this? We can start at 10:55. But what I need is this. Everybody that can make it needs to be here. Everybody that's, if you're like running in, I can just say, here you go, and get started. And I can probably go until 11:55, but I got a class coming in at noon, so I can't really do much other than that. Oh, it's econ. It's econ. I can't do anything about that. No. 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 Have I ever done that? No, but I'd like to give you as much time as possible. You got to look at this. There's 48 people in here, so just handing out 48 different exams, that takes time. So
what if we just show up at, say, 6?
You've tried that before, and it didn't work, so. All right. Any questions? Okay. One other thing I will mention. Today we are going to discuss and do an example on threaded rod design, and then that is it for exam 1, okay? Afterwards, bolted connections, welded connections, that's all exam 2. So today is going to be our last lecture of relevant concepts and topics on exam 1. So everybody's aware of that. Sound good? All right. All right, so I'm going to skip this. All right, we'll start here. So as you recall, we discussed the Hyatt Regency collapse last time. I'm going to kind of skip that because I want to get straight into the threaded rod design, and we're going to have an example that's pretty relevant. But the big thing about threaded rods is that they are inherently slender. They are meant to be slender, so we do not need to apply the L/R slenderness limit to that. Also, because of the nature of threaded rod design, we don't have to consider gross section yielding. Basically, the way that we determine our net area is we take 75% of the gross area. If you look at the table I'm going to show you here in a second, that's where the 0.75 comes from. And so if you look at the available steels for threaded rods, really you don't have to consider yielding. The only thing you have to consider is fracture. So it makes it really easy to design. Your phi value is 0.75. Your FNT value comes from a table, but it doesn't really because it's just 0.75 FU for both cases. And so that's taking into account the reduced area that you get around the threads. So you don't really have to worry about that. So it's pretty straightforward. So you take the gross area of the bar, F, which is A sub B, F sub U, and then 0.75 squared, one for the phi value and one for the reduced area because of the threads, to get phi RN. So it's pretty straightforward. So there is no slenderness limit. So if phi RN has to be greater than or equal to your factored load, you can set those two essentially equal to one another or use the inequality that I have here. It's whatever you prefer to solve for dB. And so what I did up here up top is I put everything in a fractional format, and I rearranged and solved for the dB. It's just a little bit of algebra. And so you end up getting that your minimum bar diameter has to equal 8/3 times the following radical, just factored load over FU times pi. It's pretty simple, pretty straightforward. And again, that already includes your fee value. Your fee value is built in, so you don't have to reapply it. But you do need to factor your loads. So that is something that you do need to do. Sound good? Are there any questions? All right. So what we're going to do today is a quick example on threaded rod design. I think you can kind of see where this is coming from, because this is basically sort of designed to look a lot like the Hyatt Regency collapse. We have a 6-foot wide walkway, with rods spaced 20 feet longitudinally. So from here to here along the length of the walkway, that distance is 20 feet. So if you want me to write that out, that's 20 feet. And this distance is 6 feet. I know the scale looks a little weird. I drew this in like SketchUp and I rotated it, and I drew it to scale, but it doesn't look it. I don't know why. But, oh well, we have a 100 PSF live load. We're going to assume for the sake of discussion it's already reduced. However, you're not supposed to apply live load reduction if the load gets above 100 PSF anyways, so it doesn't really matter. And so what we're going to do is we're going to design each one of these rods. So everybody good? One other thing to keep in mind, there is also the dead weight of the slab. This is a 4.5-inch thick reinforced concrete slab, and so we're going to account for that as dead load as well. Oh. Okay. So I'm actually going to copy this. So here's the walkway that we're designing. And so what I want to do is I want to use the same concept that I did before with kind of like with the block shear. I want to don't make fun of my eye. That's about the best I can do. So what we're going to do is we're going to imagine that we're in the helicopter looking down on the walkway, because we're going to do this or use this in order to perform our analysis. The only other thing I want to point out here is that is 4.5 inches. Okay. So looking down on the walkway, what we've got is we've got a walkway that, for the sake of discussion, we'll assume goes on forever. All right. And if we're looking at it from above, what we would see are these rods sort of sticking out like that. So those are the rods supporting the walkway. Okay? And so let's pick a random rod and let's draw out its tributary area, right? So its tributary area, remember, how do we define that? We define it as halfway over to the next adjacent rod, right? So from left to right, what we've got is we've got, a tributary area that comes down like this, and then the tributary rods, let's say, or tributary rods, the rods on the upper part of the walkway are going to resist all the loads on this side. These rods are going to resist all the loads on this side. So the tributary area is going to split halfway down the middle, and that is going to be the tributary area for a given rod. Does that make sense? So let's put some dimensions on this. What's that dimension right here? Not 10 feet. It's 20, right? Because remember, from here to here is 20 feet. That's from rod to rod. So halfway over is 10, halfway over is 10, that's 20. But what is this dimension right here? That's 3 foot. Okay? Because the entire walkway is 6 foot wide, so that tributary area is only going to go halfway up. So what is the tributary area going to be? It's 20 feet, 3 feet, times 60 square feet. So that's the tributary area. Sound good? So I'd argue that the easiest load to determine is the live load, okay? Because if I want to determine the live load on each rod, all I've got to do is take 100 pounds per square foot and multiply it by 60 square feet to get 6,000 pounds, or 6 kips. That one's easy. All right. But what about the dead load? Times what? You're on the right track. There you go. Times the volume, right? So what we're going to have to determine is, I'm going to do my best to draw this out. Forgive my art. But from here to here to here, here, we got to determine the volume of that concrete, right? Now, how do we determine the volume of that concrete? There you go. 20 times 3 times 4.5 inches, right? But you got to be cognizant. So now we're going to multiply that times the unit weight of concrete. So what do you think is a reasonable value for that? 150 what? Remember, you write out those units. So 150 pounds per cubic foot times 20 feet times 3 feet times 4.5 inches. Anybody got a problem with that? Units. Write them out. Use your pencil. Write the little I. Write the little N. Don't you forget to dot that I, just like I did. See which one. Bam. 1 foot, 12 inches. And so what does that come out to be? Say it again. 3375. 3375 what? Pounds. I have a second on that? So now that we got a dead load and a live load, now we can compute PU. $1.2 dead plus 1.6 live. Nope, I got that backwards. Bless you. Let's leave it in kips, and you'll see why here in a second. Oh, man, my handwriting is not cooperating. And so what does that come out to be? Okay. Okay. I want to leave this in kips because we are designing this rod, but is there anything before we do any math, do we know anything about the rod? Okay, we know it's made out of A36 steel. Now, in order to design a threaded rod, do we need FY, FU, both? What do we need? I couldn't hear that. We need FU. What is FU for a threaded rod made of A36 steel? 58 what? 58 KSI. And so that's 58 KSI. And we got that where? And so remember, bring your manual. We use it. All right. So now that we've got this, we can do the threaded rod design pretty easily. It's really not that difficult. So okay, so the threaded rod design, all we have to do is this. We take our factored load and our FU and plug it into the following. And so again, that's just taking the area of a circle, pi over 4d squared, the phi values of 0.75 and all that, and just doing some algebra and solving for dB. That's all that is. So that's 8/3 times 13.65 kips over 58 KSI times pi. So the question was earlier, I said, why did we put that in kips? This is why, because look what you got. You got kips and kips per square inch. And so what does that come out to be? So what does that mean? Use a 3/4 inch diameter rod. So just round that up to the nearest increment, and I'll pull that up here in a second. So use a 3/4 inch, and just so you're aware, if you see me write this symbol like 3/4 inch diameter rod, like if you see me write a phi value right there, that's what that means, just a shorthand for writing diameter. What's that? Just trying to help me out, right? Trying to help me out so that the grading's easier. Don't think I don't know what you do. It's tempting. All right, any questions? One thing to keep in mind, let me go back here. Right here, typically available bar diameters. So first off, whenever you get a value, you're going to round up to the nearest increment, because obviously you don't want to round down. If you're rounding down, you'd be using a rod that's smaller than what you actually need, right? That would be bad, okay? So you're always going to round up. And so anything between 1/4 inch to 1 1/4, do it in an 1/8 of an inch increment. So we got 0.73, so we would round up to the nearest 1/8 of an inch. And so that happened to be 3/4, because 3/4 is 6/8. Anything that's 1 1/4 to 4 inches, just round up to the nearest 1/4 of an inch. Okay? So if you're wondering, like, how do I round, like where do I go, that would be your best guide. Sound good? When you install threaded rods, as Trey pointed out to me earlier, make sure that they're tight. I didn't bring them with me, I apologize, but he showed me some images of some threaded rod installations in a community center, and they are very not tight. They're like sagging, so it's, yeah. They can be. So for instance, if you have like wall supports that are going horizontally, you can run threaded rods in between them to make sure that they don't sag too much. In that they're called sag rods in that instance. Usually in most building installations, they're actually installed diagonally. So you have like a column, maybe like a beam for the roof, and you have a threaded rod going this way and this way to sort of tension the building this way against wind. But they have to be tight, you know. I didn't bring the images, I apologize, but they're like this. I'll put them in my announcement slide for next time. All right, I'll remember. Yeah, they look pretty bad. So, what'd they say? They need an engineer to come and look at it. I mean, it might not be a big idea.
Why don't you go? Serve the community.
Oh goodness. I have a license, but I don't have like a business license. I don't have my COA or anything.
How good don't you have to do community service time or something for schools? Yeah.
Not that. I do plenty, believe me. All right. Okay, any other questions? Okay. Now watch. That's exam 1. Everything from day 1 till now. Exam 1. No. We got plenty of time to talk about stuff. We're talking about bolts. So let's talk about moving forward. And so this is going to be a little bit like movie time, so y'all can kind of relax. But we've been having a lot of questions and discussions about, the actual connection itself. How did you, hold on, Dr. Mike, you got this problem. Where the heck did the bolts come from? Like, you got all these bolts spaced at 4 inches or 3 inches or 2 inches. Where did that come from? Why is it like this? Why did you lay the bolts out this way? Well, now we can start talking about that, okay? And so what I want to do is I want to talk about the 2 primary types of connections that we use in structural engineering today, and that's a bolted connection and that's a welded connection. And some of you might be going, now hold on, what about rivets? And we don't use rivets anymore. We don't use rivets anymore. We used to use rivets, but we don't for 2 primary reasons. One, they're highly unpredictable. In other words, it's kind of difficult to determine the capacity of rivet A because the capacity of rivet A and the capacity of rivet B can be wildly different. But another thing, does anybody know the other reason why we don't use rivets in structural steel? Well, they're labor intensive, and that sort of feeds into a little bit of the second. Say it again. They're dangerous. Have you ever seen a rivet installed? You have to take that rivet and you have to get it in, red hot, and you stick it there and strike it on. That's kind of dangerous. Okay, and we can actually get an economically designed connection without having to worry about it because we can use either bolts or welds, so we really don't need to use rivets anymore. So the facts are, as a structural engineer, you really never have to deal with them unless you're load rating a bridge where there's rivets installed. And if you are, there are guides that'll help you determine the capacity of a rivet, and usually they're way conservative. So it's usually a lookup, so we can sort of just bypass that. You're never going to be doing a new structure with rivets. So that's what I'm sort of concerned about. Let's talk about bolts, okay? There are oodles and oodles of different types of bolts that we use in structural engineering, but I want to mention 3 of them that are the most common. Okay, first off is A307. A307 are primarily used as like temporary bolts or for secondary members. They're low carbon steel bolts. You can see them used here and there, but primarily you won't see them a lot. The 2 that you see the most are A325 bolts and A490 bolts. So I have some images here of some A325 and A490 bolts. You can tell the grade of a bolt by looking at the head of the bolt. It actually is printed A325 or A490. So it'll tell, these are ASTM specs. This is ASTM A325, ASTM A490. So I'm curious, let's take, for instance, the ASTM A490. So the A490 is the ASTM spec. Anybody have a wager as to what that is? Say it again. Exactly right. That was manufactured by Lejeune, so that's their symbol, LE. I can't remember what that one is right off the top of my head, but oh well. It's bugging me. Maybe it'll come to me, but that one's Lejeune. So, but yeah, these are that's the manufacturer. So you can always tell the grade of a bolt by just looking at it. Now, what's the difference between an A325 and an A490? Simple. A490s are a little stronger, but they're a little more expensive. And so, which one do you use? I mean, it depends, You could, if you used A490 bolts as opposed to A325, you're using less bolts, but they cost more. So where's the trade-off? Well, it depends on which one's more expensive. Steel prices can vary, so it depends. So I would say you need to assess both. I'll say a couple other things. Typically in bridges, you're pretty much exclusively using A490, especially on splices, because of the presence of fatigue. Typically, whenever fatigue's involved, your connection requirements jump through the roof. You end up needing more connecting elements or more inches of weld or whatnot. And so that just sort of is what it is. In buildings, you can see a mixture of both. So there. Now, A325 and A490 bolts are the primary grade of bolts that we use. But sometimes they're not the primary type of bolt that we use. I'm going to skip ahead like a good bit to show you. Actually, let me use my mouse. I'm going to skip ahead a good bit because I want to show you a particular type of bolt. Hold on. I kind of want to explain what's going on with these bolts. Actually, I'm going to get out of the slideshow. Okay, this right here, I want to sort of explain what's going on here. This is what's called a twist-off control bolt. To be honest, I should have put an image here at this point in the presentation. This is a twist-off control bolt. It is a very specialty type of bolt that is used in order to generate what's called a slip-critical connection. So we're going to talk about slip-critical connections later, but the short version of the story is that a slip-critical connection is trying to account for the friction that's developed between two plates in order to generate a connection. So usually when you're looking at a slip-critical connection, you need more bolts, but you end up getting a really strong, really stable connection that you end up needing for things like fatigue. In order to generate that tension that's required, there's a lot of different proprietary products that are out there. One of them is a twist-off control bolt. And so the way that a twist-off control bolt works is it's a specialty bolt that's used with a specialty wrench. So what happens is you have this specialty bolt that you see right here, and you put the nut on, and you use a single specialty wrench. And what it does is it grabs both the nut and the bolt, and it spins them in the opposite direction. And then once you achieve that required tension, it chucks off that splined end. So as an inspector, it's really easy to tell whether or not your bolts have met the required pretension, because all you have to do is look at the bolts, and if the nub's off, then it's good. The problem is that this bolt is different than a standard A325 bolt, so it has a different specification. Now, if you're writing the steel manual, let me ask you a question. If you're writing the steel manual, would you want to have capacities listed for 20, 30, 40 different types of bolts? Well, no. So what the folks who write the steel manual have done is they've taken all of the bolts that have similar material properties, like regular bolts, twist-off control bolts, you name it. And what they've done is they've organized them into a series of groups, okay? So the two primary groups that we're going to utilize in regular old everyday steel design is Group A and Group B. So Group A includes A325 bolts and all of the other similar proprietary bolts out there that have the same properties. Group B includes all the 490 bolts as well as all the other twist-off control bolts and whatnot that have similar properties. So I'm going into this because I don't want you to think that Group B bolts actually exist. Group B is just a way that the steel manual organized all of these similar bolt types. Does that make sense?
These twist-off bolts, are they tested like in the field, like when they send out a guy to test the bolt? Are they tested the same, or is it he just walks up and looks and says, yeah, I'm pro off?
Well, it's not as simple as that. What I would say is this. Number one, the bolts themselves have to meet ASTM spec before you even get them, and the wrench itself has to be calibrated. So if you got a calibrated wrench, got a calibrated bolt, then all you have to do is look at the spline. So there's a little bit more going on than that. But
So they don't go out, they don't put it in
the Skidmore?
yeah.
No, well, I'm going to mention that later. The Skidmore Wilhelm. I'm going to mention that later.
So they don't, will they use that on the twist-off bolt?
Well, they'd use it on the wrench. So,
Okay.
yeah. But yeah, what you're talking about when we get into slip critical, we're going to talk about that.
Okay.
Yep. Any other questions? So again, there is no such thing as a Group A bolt, but the manual has organized the bolts in Group A and organized them in Group B. I just want to be clear on that. There is a Group C, but they're pretty rare. They're very high strength. It's basically for seismic applications. As for diameters of bolts, bolt diameters range anywhere from a 1/2 inch to 1.5 inches, but the most common bolt diameters that we use in structural engineering applications are 3/4, 7/8, and 1 inch. Those are the ones that are the most common, period. Okay? So more often than not, most of our design problems are going to revolve around 3/4, 7/8, or 1 inch. I'm not going to make you memorize. I'm not one of those professors like, draw the bolt out and write out every single term. I'm not going to do that. I just want you, to have sort of a, you're thinking of somebody, aren't you? That's the no comment. I don't want you to, I'm not going to make you memorize every single component of the anatomy of a bolt assembly, but I would like you to have some, general terminology. For instance, when we look at shear planes, are we shearing through the threads or are we shearing through the shank? The main body of the bolt that doesn't have the threads. The grip being the distance from the face of the head to the face of the washer, and just stuff like that. I just want you to be aware of this stuff. I'm not going to make you memorize it. Okay. Sound good? All right. Now, because of the nature of a structural bolt and the way that we attach structures together, we generally generate 3 forces when we have a bolted connection assembly. Three types of forces. So we have a bolt hole, we have a bolt going through it. And so typically, more often than not, you are applying some type of shear to the bolt assembly. So you got member A, member B, you have a bolt through it, and you're yanking like that. So the bolt is experiencing some type of shear. Okay? So what are the forces that are generated? Well, I propose there are 3 forces. Number 1, you have a bolt hole, you have a bolt going through it. So the first force would be the force on the bolt. Okay? And so, think, if I have plate A and plate B and I'm yanking on it, what's the bolt going to want to do? Well, hold on. Not rotate. If you've got plate A, plate B, and a bolt through it, and you're going like that, what's the bolt going to want to do? It's going to shear in half, right? And so that's one limit state that we're going to have to assess, is the shearing capacity of the bolt. Okay? And there's a number of different variables that go into that, and I think you're going to understand that by the close of business today. But that's one. The other is the bolt bearing on the plate itself. Here's the bolt hole, here's the bolt, and so when you yank, not only is the bolt wanting to fail, but the plate is wanting to fail as well, right? Because the bolt is mashing up on the plate. And so that's force number 2. Force number 3 is if you have member number A, member number B, smack them together, you stick a bolt through. What happens when you tighten that bolt super tight? What happens to the 2 plates? They get closer and closer together, and so when you yank on them, you get friction, right? So the 3 limit states that we have to assess are really related to those 3 forces. The shear on the bolt, the bearing on the plate, and the friction between the 2 surfaces. Yes? This is the plate, and this is the bolt. Well, I'm just indicating that there's tension, that there's friction between those 2 plates. I just separated them so you can see it. So there's friction, and then there's pre-compression. So think about it like this. You have a plate A, plate B, you stick a bolt through it, and you start tightening it. What happens to the plates? They compress together. And if they compress together and develop a normal force between the 2 plates, you go like that, you got friction. That's a good question. Everybody else? Okay. All right, let's talk about the limit states that can be associated with a bolt assembly. So when I say bolt assembly, I'm keeping it simple. We're talking about a single bolt through 2 plates, yanking on them. Okay, so a couple of these limit states we have already assessed and already understand. So by now you should understand that if I have an assembly like this, it could fracture through the net section, right? That's pretty simple. It could also yield through the gross section, so these are easy. Some other ones, we could shear the bolt. We could fail the plate. Now, when we fail the plate, there are 2 different ways that could happen. One of them is that the plate itself fails sort of in a plastic fashion. The other is that the plate wants to tear out. We're going to handle each one of those. Some of these down here, like this edge failure and this bending failure, are a little more rare, and we're not going to really need to assess them for our purposes. We can also fail the bolt in tension if the bolt is actually experiencing tension. We are going to handle that later. Yes? What's that? Which one? We did, yes. That's a great point. This is the limit state we were assessing when we did threaded rods. So we were assessing it in tension. And not only that, but when we reduced the area by 0.75, we were assuming that the failure would occur at the threads and not through the shank, if you will. That's a great point. That's an excellent point. In fact, the equation was exactly the same. So, sound good? All right. Now, we have two different types of connections that we typically assess in structural engineering. One of them is what's called a bearing type connection, and one of them is called a slip critical connection. The difference between the two is that bearing type connections rely on, okay, you got bolt hole, bolt. Bearing type connections rely on the bolt literally coming into physical contact with the plate. So the bolt is bearing on the plate. So the only limit states that we need to assess in a bearing type connection are the shearing of the bolt and the bearing on the plate. Okay? Whereas in a slip critical connection, we have to assess both of those limit states as well as the friction between plate A and plate B. When you're using a slip critical connection, you generally have to use more bolts. Okay? A good rule of thumb is that slip critical connections under the same load require about double the amount of bolts as a bearing type connection. So to give you kind of an idea. Bearing type connections are a lot cheaper and can be used in most normal situations, I would say. So like a floor beam connecting to a girder, bearing type connections any day of the week and twice on Sunday. But if you ever have like a seismic application or fatigue, you generally have to detail those as slip critical. So what we're going to do is we're going to handle each of these limit states one at a time. We're going to start off by handling the bolt fracture and all of the different issues that go along with that. We don't really have to handle bearing failures because the way that bolts are constrained, it generally ends up not being a big deal, and bolt fracture ends up what governs. But we're going to handle failure of the bolt and failure of the plate, and then later on we'll talk about how you actually arrange the bolts, like how far apart they should be spaced from each other, how far apart they should be from the edge, and all of that stuff. So let's talk first about bolt shear capacity. Now before you start writing down a whole bunch of equations and expressions and whatnot, I'm going to show you a design aid that's going to make your life a lot easier here later. So first off, the design capacity of a bolt is basically some nominal shear stress multiplied by the area, and then your phi value is 0.75. Now right now, let's be clear, right now we're just talking about how much force it takes to shear the bolt in half. That's it. Okay? But there's a couple variables that we have to assess, and that's variables associated with what's called the shear plane. Okay? So what do I mean by the shear plane? Okay? Well, the first question we have to ask is, are there threads included in the shear plane? So I think this image probably explains the shear plane better than I ever could. So better than I ever could verbally. So bless you. So what I have here is an image on the left and an image on the right of that same bolt assembly. A plate, and a bolt sticking through it. Okay? And so I take those two plates and I yank them. That bolt is experiencing shear. So the big question is whether or not the threads are included in that space between the plates, which is what we call the shear plane, or whether or not they're excluded. Yes? Well, that's a good question. It's not really a matter of whether or not I want to include them. It's whether or not they're there, whether or not I like it or not. Think about it like this. There's only so many bolts and so many plate thicknesses, right? So you use that bolt in this scenario. Are the threads there or not? Well, it depends. Now, how about this? Which one's weaker? Threads included or threads excluded? Included. Okay? Now, let's say I gave you a problem and I said, I got this member and it's connected with A325 bolts. And I didn't tell you whether or not the threads are included or excluded. What would you do? But let's say you couldn't look it up, or so let's say you didn't know, or I didn't give you the specific length of the bolt. Because in order to determine this, you need some more information than just that. You need the length of the bolt, you need a couple other things. If I didn't tell you, what would you do? Assume they're included, right? So that's sort of the point I'm making, is that unless I tell you and you don't know, assume that they're included, because that's going to be the worst case scenario, right? Okay? Us structural engineers, we're clever, so we come up with a naming convention. So if you ever on a homework assignment or an exam or anything like that, if you ever hear me use the term, like if I say I have a 3/4 inch bolt and it's group A in, what I mean is that it's a group A bolt and the N means that the threads are included. If I say group AX, I mean that the threads are excluded, okay? So we're clever, aren't we? So just so you're aware, if you ever hear me use those terms, that's what that means. Now, whether or not you're using a group AN or a group AX bolt, let me go back, that changes your FNV value. Remember how we said that threads included are weaker? Well, let's go to table J3.2 on page 16.1-129. Because it's a little small on the slide. And so what happens, so let's look at this. If you look here on the left, there are 2 rows associated with group A. One is where the threads are included, and one is where the threads are excluded. Instead of saying included, it says not excluded. But look right here. First off, do you notice how the tensile capacity doesn't change? Because that doesn't matter. Here's my bolt. The tensile capacity is yanking on it this way. It doesn't matter whether or not the threads are included or excluded in the shear plane, because when you're applying tension, you're not shearing it, so the shear doesn't matter. So the tensile capacity is independent of that. However, if you look at your FNV values, the FNV values are changing. If the threads are included, the FNV, the nominal shear stress, is 54 KSI. As opposed to when the threads are excluded, it's 68 KSI. So the bolt gets stronger when you don't put threads in the shear plane. And that's how we incorporate that. Make sense? That's pretty easy. The other thing we have to address is this. What happens if there are multiple shear planes? Right? How do you handle that? Well, it's pretty simple. The bolt up top is what we call a single shear situation. So a plate, shear. The plate on the bottom is under double shear. Okay? On the bottom, this would be probably something you would see if you had a spliced connection. It's very common to see double shear situations in that. If you ever have a situation with double shear, the capacity is double. Okay? And it's not because the bolt magically got twice as strong. It's because in order to shear that bolt, you have to rip through twice as much material. It's not because the bolt got stronger. It's because there's more material. So if you ever look up the capacity or compute the capacity of a double shear bolt, it's twice that of a single shear bolt, just because there's more material. Yes? Mm-hmm. That's a good question. The answer is no. No. But filler plates can affect slip capacity, the friction. And you're going to see a variable about that here in a little. Like when we talk about slip critical connections, you're going to see a variable on filler plates. So if you had like a weird gap between 2 flanges, like 3/16, and you met that by using 2 plates, like 2 filler plates, then you can have a reduced slip capacity as a result. And we'll look at that here in a little bit. So. Everybody good? Now, this is going to make your life a lot better. I want to look at page 7-22. Notice how I put my little green star in there. This is one you should tab, just right off the bat. And so I want to show you how these values are computed, just so you're aware. I don't want you to think that this is a mystery. Watch this. Okay, I'm making up a value. Let's say we have an A325 bolt with the threads included, and it's single shear. Okay, and it's 3/4 inches in diameter. What is the capacity of that bolt, just looking at the table? It's a 3/4 inch diameter bolt, single shear, A325. Remember, what is A325? Is that Group A or Group B? There we go. So watch this. Group A, threads included, single shear, 3/4 inches in diameter. What's the capacity? 17.9 what? Kips. So the PRN is 17.9 kips per bolt. Now, do you want to know how they compute that value? Here's how they compute that value. All right? Let's look at this. Group A, threads included, FNV is 54 KSI. So what we're going to do is we're going to say phi FNV AB is 0.75, 54 KSI, and then the area of a bolt, pi over 4, 3/4 inches squared. And it's single shear, so we'll multiply it by 1. What is that? It's 17.9. Cool stuff, right? So, just to be clear, okay? Just to be clear, what we're doing here in this table is we're just looking at bolt diameters, nominal shear stresses, and shear conditions, and we're just opening up a big Excel sheet and plotting it out. See, look at the difference between single shear and double shear. What's the difference between the 17.9 and the 35.8? It's double because there's 2 shear planes. So the point I'm making, you don't ever need to compute the shear capacity of a bolt. It's right there. Keep in mind, we're using the blue numbers, not the green numbers. We're using LRFD, okay? So we are only using the blue values. Sound good? Okay. Now, what we're going to do next time is talk about this, okay? So in order to determine the capacity of a bolt, it's pretty simple. Take that, multiply it by the number of bolts, boom, there's the bolt shear capacity of your section. Easy peasy. What we're going to do next time is we're going to talk about failure of the plate, okay? In other words, a bolt bearing failure. Now, there's 2 different ways that a bolt bearing failure can occur, and this is an image of a steel connection to show you that. The first one is what's called bolt tear out. So basically the bolt actually fracturing along the bolt lines. This is kind of similar to a fracture block shear type failure. Then the other is bolt hole ovalization. It's where the bolt hole sort of plastifies and it just kind of stretches and stays that way. This is kind of similar to yielding. Now I'll go ahead and tell you, this has a mechanistic derivable equation. This does not. This is sort of empirical, goes off the test data as close as possible. Here it is. We're going to derive those expressions and simplify them next time. Then we'll start looking at bolt spacing and some example problems. That's all I got.